Dear students, in this video we are going to study about energy and power in electrical circuits, electric cells and batteries, electromotive force and internal resistance of cell, and finally determination of internal resistance of a cell. Discuss about energy and power in electrical circuits. When a battery is connected between the ends of a conductor, a current is established. Battery is supplying energy to the device which is connected in the circuit. Let us consider a circuit in which a battery of voltage V is connected to the resistor as shown in figure 2.15, like this. Here is a battery of voltage V and here is the resistor of resistance R, and a current I will flow through the resistor R from the battery. Assume that a positive charge of dq moves from a point A to B through the battery and moves from point C to D through the resistor and back to point A. When the charge moves from point A to B, here there is point A and point B, it gains potential energy du equal to V dq, and the chemical potential energy of the battery decreases by the same amount. When this charge dq passes through resistor, it loses the potential energy du, that's given by V dq, due to collision with atoms in the resistor, and again reaches a point A. This process occurs continuously till the battery is connected in the circuit. The rate at which the charge loses its electrical potential energy in the resistor can be calculated. The electrical power P is the rate at which the electrical potential energy is delivered. So P is given by du by dt, and that's given by V dq by dt, that's equal to V dq by dt. But this expression dq by dt is equal to the current, electric current I, and therefore this equation can be written as P equal to V times I. So this expression gives the power delivered by the battery to any electrical system, where I is current passing through it and V is the potential difference across it. And the SI unit of electrical power is given by watt, where 1 watt is equal to 1 joule per second. Commercially, the electrical bulbs used in houses come with a power and voltage rating of 5 watts, 220 volts, 30 watts, 230 volts, 60 watts, 230 volts, etc. And here is a picture of electrical bulbs with the power rating, and here it is about 10 watts, whereas here it is about 60 watts. Usually these voltage ratings refers AC RMS voltages. For a given bulb, if the voltage drop across the bulb is greater than the voltage rating, the bulb will fuse. Using Ohm's law, power delivered to the resistance R is expressed in other forms as P equal to IV or I into IR, that's given by I square R. And also P is equal to IV, that's given by, for substituting for I, we can write this expression as V by R into V, that's given by V square by R. So here in this case the power is directly proportional to the square of the current, and here in this expression the power is directly proportional to the square of voltage. And the electrical power produced that is dissipated by a resistor is given by I square R. It depends on the square of the current. So hence if the current is double, the power will increase by 4 times. Similar explanation holds true for voltage also. And the total electrical energy used by any device is obtained by multiplying the power and duration of the time when it is on. If the power is in watts and the time is in seconds, the energy will be in joules. In practice, electrical energy is measured in kilowatt hour, that is 1 kilowatt hour is known as 1 unit of electrical energy. As given by this, 1 kilowatt hour is equal to 1000 watt hour, that is 1000 watts into 3600 seconds. That's given by 3.6 10 power 6 joules. And this expression P equal to VI, you can remember this expression, and if you want to calculate the value of potential energy, then that's given by that P by I, and I is given by P by V. So you can remember this expression by using this. Here you can write V into I, P, and here I, and here and say P. Hmm. So if you want to calculate the value of P, you can multiply the voltage and current. And if you want to calculate I, you can divide the value of P by V. And if you want to calculate V, the voltage, divide the value of P by I. We are going to study about electric cells and batteries. What is an electric cell? An electric cell converts chemical energy into electrical energy to produce electricity. It contains two electrodes, carbon and zinc, immersed in an electrolyte, which is sulfuric acid, as shown. Several electric cells connected together form a battery. When a cell or battery is connected to a circuit, electrons flow from the negative terminal to the positive terminal through the circuit. By using chemical reactions, a battery produces potential difference across its terminals. So this is an electric cell, and this potential difference provides the energy to move the electrons through the circuit. Commercially available electric cells and batteries are as shown in this diagram. Electric cells and batteries. Now let us see what is an electromotive force and internal resistance of a cell. A battery or cell is called a source of electromotive force, EMF. The term electromotive force is a misnomer since it does not really refer to a force, but it describes a potential difference in volts. The EMF of a battery or cell is the voltage provided by the battery when no current flows in the external circuit, and it is shown in the figure 2.19. Electromotive force determines the amount of work battery or cell has to do to move a certain amount of charge around the circuit, and it is denoted by the symbol epsilon. So how to measure the EMF of cell? That is given in this diagram. In an ideal battery, it has zero internal resistance, and the potential difference across the battery equals to its EMF. In reality, the battery is made of electrodes and electrolyte. There is resistance to the flow of charges within the battery, and this resistance is called the internal resistance R. For a real battery, the terminal voltage is not equal to the EMF of the battery. A freshly prepared cell has low internal resistance and it increases with aging. Next, we are going to study about the determination of internal resistance. How this internal resistance of a cell is determined. The circuit connections are made as shown in this diagram, like this, and the EMF of cell epsilon is measured by connecting a high resistance voltmeter across it without connecting the external resistance R. Since the voltmeter draws very little current for deflection, the circuit may be considered as open, since the voltmeter reading gives the EMF of the cell. Then the external resistance R is included in the circuit and current I is established in the circuit. The potential difference across R, the resistance, is equal to the potential difference across the cell, V, as shown in this diagram. The potential drop across the resistor R is given by V equal to IR by Ohm's law. And due to internal resistance R of a cell, the voltmeter reaches a value V, which is less than the EMF of a cell, epsilon. It is because certain amount of voltage, R, has dropped across the internal resistance R. Then V is given by epsilon minus IR. So IR can be written as epsilon minus V. And dividing the equation by the equation 2.35, we get IR by IR equal to epsilon minus V by V. Therefore, R is given by epsilon minus V by V into R. Since epsilon V and R are known, the internal resistance R can be determined. So we can also find the total current that flows in the circuit. Due to this internal resistance, the power delivered to the circuit is not equal to the power rating mentioned in the battery. For a battery of EM of epsilon with an internal resistance R, the power delivered to the circuit of resistance R is given by P equal to I epsilon, and thus given by I into V plus R. Here V is the voltage drop across the resistance R, and it is given by IR. Therefore, P equal to I into IR plus IR, and that can be written as P equal to I square R plus I square R. Here this I square R is the power delivered to the internal resistance and I square capital R is the power delivered to the electrical device. And the resistance is given by R. For a good battery, the internal resistance R is very small, then I square R is very much less than I square R, and almost the entire power is delivered to the external resistance.